let me introduce today's speaker. We have the pleasure of listening to Timothy Proctor, who is a staff scientist at the Quantum Performance Laboratory at Sandia National Labs. His primary research interests are quantum computer characterization, benchmarking, and verification. Prior to joining Sandia, he obtained his PhD in 2016 from University of Leeds in the UK, where he developed a theory of quantum-enhanced sensor networks. And today he'll be talking about some of his recent work about measuring the capabilities of quantum computer. So Tim, please take it away.
Thanks for the introduction. So yeah, I'm Timothy Proctor. I'm going to be telling you today about a few different projects we've had over the last few years that can all come under the heading of measuring the capabilities of quantum computers. So as a brief outline, I'm going to cover 3 different topics. So first of all, I'm going to tell you about some results we published in Nature Physics at the start of this year on measuring the capabilities of quantum computers. So there, I'm going to tell you about what we mean by a quantum computer's capability. Then I'm going to tell you about mirror circuits, which is an efficient method that we developed for probing capabilities. And I'm going to show you some experimental results briefly of using these techniques. So then in the second part of the talk, I'm going to very briefly tell you about some scalable randomized benchmarking methods we've developed using randomized mirror circuits. So this work is in these 2 papers that are out on arXiv. And then finally, I'm going to be telling you about how we can efficiently verify the results of an algorithm using a mirror circuit-based protocol. So the idea here is that we can measure the process fidelity for which an algorithm has been implemented by running a particular family of mirror circuits that we developed. And this is results that came up fairly recently on arXiv. So first of all, I'm going to focus on this work on measuring the capabilities of quantum computers. So first up, some very basic terminology, just to make sure everyone's on the same page. I'm going to be talking a lot about quantum circuits. I'm sure you all know what a quantum circuit is, but just in case you use some different terminology. A circuit has a width, and that's the number of qubits involved in the circuit, has a depth, and that is the number of layers of logic gates. And throughout this work, it's pretty important that circuits have barriers in them in the IBM Qiskit language, meaning that you shouldn't compile together the layers of a circuit. So you have to run each layer in turn. So all of this work is motivated by a pretty high-level question, which is that people really need to know what a quantum computer can do. So someone might be trying to sell you their quantum computer, sell time on their quantum computer, or just persuade you to collaborate with them and run some experiments on their hardware. And before you do that, you want to be able to answer questions like what applications or algorithms can this quantum computer actually run? There's lots of things you might want to do. You might want to run, say, random circuit sampling and get a nice snazzy Nature paper. You might want to demonstrate quantum error correction, see how well your error corrected code works. You might be interested in trying out some new NISQ algorithm you developed. All of these things have different characteristics, and it's not obvious that a device that can implement one well can implement another well, and so on. This is a really complex and multifaceted question, answering what algorithms or applications can you run. So we focus on a slightly simpler question that will allow you to answer that broader question, which is we're going to focus on answering what circuits can a particular device run successfully. So I come to you with a circuit, and then we want to be able to answer, can this device run that circuit or not? So can it run it with high fidelity? So in order to start answering this question, we need to know what we mean by a quantum computer successfully running a circuit. And so I have some quantum circuit I'm interested in running, and we could simulate this on my imaginary perfect quantum computer. So you can do a brute force simulation, and then you can see what distribution over bit strings you'll be sampling from if you did run this on a perfect quantum computer that you obviously don't have access to. If you run this on a real quantum computer, you're going to get samples from some other probability distribution. And in general, these 2 probability distributions are not going to be exactly equal because errors occur when circuits are run on real quantum computers. So for example, each of your gates might slightly over or under rotate, or there may be stochastic errors that cause a bit flip with some probability to occur, and so on. And so at a high level, we can quantify success probability, how well can we run this circuit, as the distance between these distributions. And that is not a single well-defined concept. There are many ways you could quantify distance, but that's the general idea of what we're trying to do. So this allows us to formalize our concept of a quantum computer's capability in terms of what we call a capability function. So it's a map from the space of all possible circuits you could run on a device to how well that device runs that circuit, so to the success rate for that circuit. So it's this function f for a particular device that maps a circuit to the success probability for that circuit. So for example, this could be quantified by process fidelity or some other metric for success. And so everything I'm talking about here is aiming to probe this capability function. We want to be able to understand this capability function for a device. But you can't just measure the capability experimentally because you can't evaluate this function even for just a particular circuit. So if you have some, say, large computationally useful circuit, perhaps you're trying to demonstrate quantum advantage on some problem and you have a circuit that should do that, and you want to know, like, what is the process fidelity with which this particular hardware will run that circuit. So to directly evaluate this capability, what you have to do is you have to do a slow simulation that could potentially take millions of years on even a huge supercomputer. You have to simulate this quantum circuit on a classical machine to work out what the true ideal output distribution is. And then you also have to run an experiment that will potentially also be really slow to estimate the probability of distribution you get out of an experiment. And it can be very slow because it's going to be a very high entropy distribution. So to estimate a high entropy distribution, you need a lot of samples. And so this can be an extremely painful process and often completely intractable to do this. And this is actually at the root of how lots of benchmarking methods that currently exist work. They basically use these two procedures. So for example, cross-entropy benchmarking, quantum volume, lots of algorithms of benchmarks and so on. So this is a pretty problematic issue for testing quantum computers. So what I'm going to be telling you about is a technique we've developed called mirror circuit benchmarks that take a potentially computationally useful circuit, so an arbitrary circuit, and they turn them into some different circuits that you can run in a fast experiment, and you can simulate what you should get out using very easy simulations that are pretty much trivial to do. And from these results, you can infer the value of the capability function for this circuit. So we can indirectly assess how well you can run that circuit. So I mentioned mirror circuits. So what are these? So they are based on a really simple idea. So you take your circuit, whatever it is, and then you follow that circuit by the reverse of that circuit. So you just run the circuit backwards with each gate replaced with its inverse. This is an incredibly simple idea, and it has a very nice property, which is that whatever you put into the circuit, you should get back out again. So if you input all your qubits in the all zero state, which is a standard initialization, they should all come back in the all zero state if you run that circuit perfectly. And so this is very naturally a property that's useful for a benchmark. We have an efficiently verifiable output. We see all zeros, it was successful. If we see something else, we know something went wrong in that instance of running the circuit. This simple idea, though, is flawed because of error cancellation. Because eventually what we're doing here, this is a loss and echo, and what that does is it tests your ability to reverse an evolution, not whether or not you did the correct evolution. So there's a very extreme example that demonstrates this. Imagine your quantum computer is broken, and when you press the buttons to do gates, it does nothing at all, and your qubits just sit there idling. Well, you will get out exactly what you put in. You put all your qubits in zero, all your gates fail to do anything at all, you get your qubits back out in zero. You will get a perfect score in a benchmark like this, but you've utterly failed to implement the circuit you're interested in. And although that's an extreme example, you can come up with small errors. That's a huge error. You come up with small errors that get cancelled out by this kind of echo, because this is an echo experiment. They echo out certain kinds of errors. So this is flawed, but we decided that there's actually a way to fix this by just some simple adaptations to the technique. So what we do is we insert a randomized central circuit. So we insert a small subroutine into the middle that is randomized, that prevents systematic cancellation of the errors in the first half and the second half of this circuit. And then we also insert a randomized state preparation circuit that allows us to probe the performance of this circuit on general input states rather than just the all zeros input state. And then we undo that randomized state preparation with the randomized measurement layer at the end. And then we do some tweaks to the inverse layers to make sure that this whole thing still collapses down to something that we can easily simulate, so that we should always get out a particular bit string that we can easily calculate. And it's not obvious how you do this in general. We have a prescription for how you do this for arbitrary, almost arbitrary circuits in the first paper that we had out on this. Right now, I'll tell you about how you do it with Clifford circuits, and then towards the end of the talk, I'll tell you how you do it in a particular way with completely arbitrary circuits. And so if you had Clifford circuits, so this circuit just contains Clifford gates, then in the middle, you can insert just a layer of random Paulis, and then your quasi-inverse is just the inverse. You just invert your gates, and that whole thing is a Clifford, random Pauli, inverse of the Clifford. That just composes to another Pauli, and then the state preparation and measurement are just uniformly random local Cliffords, and that whole thing composes to a Pauli that we can easily compute, and we can prove that this circuit ensemble also has nice properties. In particular, as well as an efficiently verifiable output, a process performance on circuits sampled randomly from this ensemble can be used to infer the fidelity with which we can perform this original circuit C. And I'll get back to a more formal statement of that towards the end of the talk. So I've given you the idea of mirror circuits, but now I'm going to show you some experimental results of what kind of things you can do using these kind of benchmarks. So this is the kind of investigations you can do of real-world hardware using specific benchmarks built from this circuit mirroring procedure, which can be used to generate benchmarks of pretty much any type you like. So what we've done here is volumetric benchmarking. So that means you vary the circuit width and you vary the circuit depth. So the idea of volumetric benchmarking, and with randomized and periodic mirror circuits. So here's a picture of what a randomized mirror circuit means. It means what you think it would. It includes a random circuit, and then you reverse that random circuit. And so what I'm showing you here is the results of volumetric benchmarking of 12 different publicly accessible devices from a few years ago. And so each different grid here is for a different device. And what we're showing is the performance as you vary the circuit width and the circuit depth of random circuits. And we're showing information about the maximum, mean, and minimum success probability. We're pulling polarization, which is very closely related to success probability, as you vary the circuit width. And this allows you to compare different devices and also to learn things about the kinds of errors going on in these systems. I'm not going to go into what we can learn from these kind of plots due to the time constraints here. I'm going to talk about a different, simpler plot that we think is really useful for doing high-level summaries of this kind of data. So this is what we call capability regions. And the idea here is it's meant to be an easy to understand summary of a device that is also contains lots of really useful information about how well a device works. So the idea is that for each device, we split the width depth plane into 3 regions. One of them, the green region, in which all circuits of that shape have succeeded in our experiments, an orange region in which some succeeded and some failed, and a white region in which they were all failing. And so you have to create one of these, you have to set some criteria for what it means to succeed or fail. We're choosing a threshold of 1/e for our success probability. And so if you came to me with a circuit that shape was somewhere in the green region, I would tell you that's really likely to succeed. If it's in the orange region, we really can't tell. It depends on the details of that circuit, depends on its structure and how that interacts with the structure of the errors in the device. So you might have to run it and see. And if it's in the white region, you're pretty much guaranteed that circuit's going to fail. So we think these are really nice high-level summaries of how well these devices perform. So now I'm going to tell you a bit about some more quantitative analyses that we can do using variants of this these mirror circuits. So I'm going to very briefly tell you about how we can do scalable randomized benchmarking using mirror circuits. The results are in these 2 papers. It's going to be very brief, so if you want to hear more about it, please ask me questions or take a look at the papers. So the idea is that we can do scalable RB using randomized mirror circuits. And so what we mean by doing scalable RB is that we can estimate the average gate error rates from running randomized mirror circuits. And we can do this in a scalable way, so we can do this on lots of qubits. And so the basic idea is very similar to standard RB, if you're familiar with that. All we have to do is some simple processing on the output data, so we get success probabilities from random mirror circuits. We do some slightly subtle processing that I'm not going to go into because it's not super important really. And then you fit it to this data to an exponential to estimate average gate error rates. So on the right here is showing results of doing this in experiments, and I'll use this to go into a little bit more detail of exactly how this works. And so the top ones, what I'm going to focus on, this is MRB, our new technique. We're comparing it to existing techniques below. And so what we've done is you sample random mirror circuits with various different depths. So that's what the x-axis is here. And then you run a bunch of different random mirror circuits, each of the depths you've selected. So that's what these violin plots show here. It's the distribution over this summary statistic that we calculate that's very similar to success probability for all of the different random mirror circuits we ran. And then this is the mean here of those random mirror circuits. And then we fit this mean to an exponential. So that's what the curve is here. And this is an exponential because we're showing this on a log scale. That's why it looks slightly funny. And so what you can see here is we were able to successfully benchmark 1, 2, 3, 4, up to 5 qubits using our technique. And the comparison down here to B and C is what you get using more standard techniques. So the bottom one is the kind of RB that is most well-known, standard RB of the Clifford group, that's pretty ubiquitous, used by almost every experimental group in the world. And the key difference to notice here is that the benchmark depth 0, so that means the shortest circuits you can run in the convention we're using in this work. You can see that the standard RB polarization or success probability, depth 0, drops off precipitously as you increase the number of qubits. So you see this blue line here is the 5 qubit case, and you just get this basically useless data. It's all just like a flat line at 0. And the reason you're getting this is that standard RB uses circuits of size n squared over log n. It's running random Cliffords from the n-qubit Clifford group, so they're the 5 qubit Clifford group. So we get this precipitous drop off in success probability for these circuits. Whereas MRB, we're not doing these kind of large subroutines, and so we only get this linear drop off, which is basically related to the drop off in a readout fidelity as we increase the number of qubits. And so we're able to benchmark a large number of qubits using this technique. So I'm claiming it scales to hundreds or thousands of qubits. Really only depends on the error rate of the qubits. And that's going to set how many qubits you can benchmark using this technique. Obviously, this experimental demo is 5 qubits. That's nowhere near hundreds. So I'm going to quickly show you some simulations that we did on up to 225 qubits to demo that the technique works on that many qubits and that we're getting the correct result out from doing it. So what I'm showing on the x-axis here is the truth. This is what we want to be estimating, the average error rate of n-qubit circuit layers. It's called epsilon omega here. And then on the y-axis, I'm showing what our method, the result you get out from our method. So what this R omega is the error rate you get out from running our technique. And each of these different points is a different instance of running our technique on a different set of random circuits in a different noise model. And we're doing simulations up to 225 qubits. What's being shown here is that we are, in most instances, getting a very good estimate of the true average error rate of our gates. So if everything's sat exactly on the x equals y line, we'll be doing perfectly. Things aren't exactly on there, and there's in fact a slight bias in our estimate. We're slightly underestimating the error rate. It's not a big deal because really RB is mostly used as to give you a general idea of how good your gates are rather than like a really detailed diagnostic. So we don't think this is a huge deal, but we also know how to fix it. We know why it's happening, and we also know how to get rid of this bias now. So finally, I'm going to tell you about this technique we've developed for efficient verification of an algorithm's output using mirror circuits. These are results that are in this fairly recent archive paper. So the high-level question we're trying to answer is if you have some potentially computationally useful circuit, you have some device you want to run it on, you need to know, am I going to get a low error output from this? Because you might want to know, have I demonstrated, say, quantum advantage on this problem? There's a variety of neat techniques that already exist for answering this question. So there's things like cryptographic prove or verify protocols. There's the trap circuit techniques of Verisin et al. And there's very special purpose techniques, such as this method from Ryan Bemick that allows you to verify anti-concentrated states. But all the existing techniques have some challenges. They're either really difficult to implement because they require complicated interactions between a prover and a verifier, or they only work under limited circumstances, such as the anti-concentrated states. So we want something that works for general circuits and doesn't have really any overhead to implementing it. So this is how our technique works. It involves running a bunch of different mirror circuits. It looks fairly complicated because it involves a lot of different ingredients, but actually the sort of reasoning behind how this works is not actually all that complex. So we have some target circuit, this is the thing whose fidelity we want to estimate. Here is a 3-qubit circuit, but this works on any number of qubits. It's just hard to draw very large circuits. And we create a bunch of ingredient circuits that we're going to compare this against. So what we do is we can construct a randomly compiled version of our circuit. And the reason we do that is randomly compiled circuits have stochastic errors, and that means that errors accumulate in really easy to understand ways. We also construct a randomly compiled inverse circuit. So this is a reverse circuit that's also randomly compiled. And then we have these same state preparation and measurement circuits that we've been using throughout and that I've been mostly glossing over. And we put these together into 3 different circuit ensembles. So first of all, we have this mirror circuit that consists of our randomized state preparation, our target circuit, followed by a randomly compiled inverse. We then have a second ensemble that consists of, again, the state preparation. It's the same as the first one, except we replace our target circuit with a randomly compiled version of it. And then finally, we just have circuits that are randomized state prep and measurement. And the reason we do all of these is basically just we want to do some basic algebra to isolate the fidelity of this subroutine here, the thing that we care about. And so what's going on here is that the success probability of this circuit, which is something we can easily evaluate in experiment, is approximately equal to the fidelity of the state prep and measurement times the fidelity of our target circuit times the fidelity of the randomly compiled inverse. And for general circuits, this isn't true. Fidelities don't decompose like this because of interactions between errors in different parts of circuits. But because we're doing randomized compilation in all of the subroutines except our target circuit, this prevents systematic addition of errors between the different parts of the circuit, and essentially just allows you to multiply fidelities or add up error rates. So our second circuit, basically the motivation behind this is this first formula here. We have 3 unknowns. We can measure this success probability. And it's the product of these 3 unknowns, and we're trying to isolate one of them. So we just need to know what these other 2 unknowns are. So we just designed 2 other circuits that allow us to isolate them. So this first one just includes the randomly compiled circuit instead of the original circuit that we're interested in. And this follows the same logic that the success probability is the product of fidelities. And so then we end up with the product of fidelities, and the randomly compiled target circuit, its fidelity is equal to the randomly compiled inverse circuit. And this wouldn't be true without randomized compilation, but it is true when you have this, because error rates just add when you have randomized compilation. And so we have this nice relationship here. And then finally, our spam circuit, we just end up with the fidelity of the state preparation and measurement operation. And if you take these 3 formulas here, you can see that with some pretty simple algebra, we can just isolate the fidelity of the circuit we're interested in. So it's this exact equation here that allows us to do that. So we can just estimate all of these success probabilities by running randomly sampled circuits from these ensembles. And then using this formula, we can approximate the fidelity of the circuit we care about. We actually use a slightly more complicated formula for a few reasons, some of which are interesting, some of which aren't. For example, some of these changes in this formula are just due to really uninteresting dimensionality and constants that essentially disappear when n is large. And we use this thing called adjusted success probability instead of success probability. That is a bit more consequential. I don't really have time to go into it. It's not super important. So I'm now going to use some simulations to demonstrate why it works, as we don't really have time to go into any more hardcore theory on this. And so what I'm showing here is simulations of applying this method to QAOA circuits on 1 to 8 qubits simulated under various noise models. So each of these plots here shows a different category of noise model. So for example, here we look at just stochastic errors, and then the x-axis is the true circuit fidelity. The y-axis is what we get out by running our procedure. And so we want all the data to sit in the x equals y line. That means we've completely succeeded. And then each of these different data points just consists of a different QAOA instance. So I just picked a new QAOA circuit, and then I've calculated the true circuit fidelity under the noise model that we picked for that circuit, and then what we get out by running the procedure. So you can see with stochastic errors, we're bang on. We're absolutely nailing the fidelity. With some of the other, particularly with just Hamiltonian errors, our estimates are a little bit more off from the true result, but they're still pretty well clustered along the x equals y axis, x equals y line, and we know why we would expect to get worse performance there, because we're relying on the theory of randomized compilation, and that's a little bit more shaky in the case of Hamiltonian errors. So there's more approximations involved in the theory in that case. Also claims that this is scalable, so I'm just going to very quickly show you some simulations on up to 100 qubits. So this again is QoA circuits, but we have restricted the angles in them so that they're Clifford, and that allows us to do efficient simulations. And again, I'm showing you the true fidelity versus the estimate, and we're getting pretty bang on this X with Y line, and we're also able to do this with very few samples. In fact, in our paper, we show that the complexity of the sampling doesn't increase with the number of qubits, it's independent of it. And we're doing this with only 200,000 samples for each data point, which is very practical in experiments. Okay, I'm just going to very quickly summarize. A quantum computer's capability is difficult to predict or measure. We have introduced this technique called circuit mirroring, which allows you to convert an arbitrary circuit into an efficiently verifiable circuit. You can use it for scalable benchmarks built from any circuit, such as an algorithm. You can use it for scalable randomized benchmarking, and using a particular way of constructing these mirror circuits, you can measure the process fidelity, which a circuit can or has been implemented. If you want to read more, there's these 4 papers to take a look at. I'd just like to say, obviously, there's lots of other people involved with this work at the Quantum Performance Lab. Thanks for listening, and also if you're interested in working in this area, we have open postdoc positions and open staff positions at the Quantum Performance Lab. If you're interested in that, please get in touch with me or anyone else at the QPL. Thanks very much.
Thank you, Tim, for amazing talk. So if anyone has any question, I think we have time for at least a couple of questions. So feel free to unmute yourselves and ask.
I have a very trivial question. Hi, I'm Varun. I hope I'm audible.
Yeah.
Okay, I have a very trivial question. What does one mean by randomized compilation?
Good question. Yeah, I basically assumed you knew what was meant by that, which wasn't super helpful of me. So what I mean by randomized compilation is a particular procedure that involves inserting random Pauli gates into a circuit. So the way that this works is that if you have a circuit written in this form, where you have single qubit gates and 2 qubit Clifford gates, so that's all your circuit consists of, interleaved single qubit gates and Cliffords, so say a C0 gate. And then what you do is you insert a uniformly random Pauli on each qubit after the single qubit gate, and then you insert the inverse of that before the next single qubit gate, but commuted through the C0. So you commute it through and put whatever Pauli that becomes here. And then you do the same again and so on. And then obviously this is trivially the same thing, but you compile them in. So this is all compiled together into a new single qubit gate. This is all compiled together into a new single qubit gate, and so on. And then each time you run the circuit, ideally every time you run the circuit, you redo the randomization. That's not strictly necessary. There's you can just do a single randomization, and that still has lots of the properties that you get from randomized compilation, but ideally every single instance of running the circuit, you use new Paulis.
Okay, all right, thanks.